Hi everyone, in this video we are going to discuss global changes of temperature. So what's really cool about this is we can use ice core samples to determine our temperature as well as determining our concentration of carbon dioxide. But for our concentration of carbon dioxide, we actually examine the trapped air bubbles within the ice core samples, whereas for global temperature measurement, we are looking at the ratio of hydrogen to deuterium. So before we dive deeper into this conversation, let's just review very quickly the difference between hydrogen and deuterium. So hydrogen has 1 proton and 0 neutrons in its nucleus, whereas deuterium has 1 proton and 1 neutron. So because it has an extra neutron, it is inherently heavier. So regular old hydrogen would be the lighter isotope, whereas deuterium would be the heavier isotope. Now I'm discussing this because it is very important when we actually look at these water molecules. So we have 3 different water molecules that could be frozen in these ice core samples. The first one is the simplest. It would be if you have regular old hydrogen on each one of these. The second water molecule would have 1 hydrogen and it would have 1 deuterium. The last example we could have would be if this water molecule has 2 hydrogen atoms. So inherently, this one has to be the heaviest out of the 3 water molecules, and the one on the far left would be the lightest. So what we need to talk about is their rates of evaporation and rates of condensation. So when all 3 of these are in the liquid state, the heaviest molecule is going to require the most amount of energy to get it to go from the liquid state to the gaseous state. When it is heavier, it just needs more energy to do that, to go up higher. So what we could say is out of these 3 molecules, the heaviest one is going to evaporate the slowest. Now, the same argument goes for the reverse. So now if all 3 of these are in the gaseous state, the heaviest one requires the most energy to stay as a gas. And so because it is so heavy, it doesn't stay as a gas as very long. And so it almost immediately tries to condense and go back into the liquid state. And so even though it evaporates the slowest, it condenses the fastest because it's just going to do anything it can to not be in that gaseous state. So it evaporates the slowest and it condenses the fastest. So what that really means is that out of these 3 molecules, the one with 2 deuteriums is going to want to stay as a solid and a liquid more so than the other 2 molecules. So what that really means is that our ice core samples are enriched with deuterium. So we use these ice core samples to essentially measure the ratio of hydrogen to deuterium, and we can then determine the corresponding temperature, which is kind of neat if you think about it. Okay, so now let's talk about what we've learned. That's the technique, that's how we figure out our temperature, but what have we learned? Well, essentially, we've seen that in the past 120 years, we have seen a global temperature increase of 0.4 to 0.8 degrees Celsius. Now, most people look at that and they go, less than 1 degree? Why is this a big deal? Why are we even talking about it? Here's the thing, this is the global average. So across the globe, we've seen an increase of about 1 degree Celsius. In certain parts of the world, that has been significantly greater. And so we're going to talk about that in just a second. But the one thing I want to point out is that we've been measuring this information since about the 1880s. So let's just say through 2015, because that's what we are now. So now, 9 out of the 10 hottest years since 1880, okay, 9 out of the 10 hottest years have occurred since the year 2000. So just in case that didn't make sense, in the last 15 years, we have had 9 out of the 10 hottest years since we've started measuring temperature back in the 1880s. That is a lot. We have seen a significant increase in our temperature here globally, and that's very, very important. So don't forget about that one fact when you try to get rid of and try to negate this and say, it's just 1 degree. We need to focus on this. It's not just 1 degree. We're seeing a significant increase in our global temperature. So let's look at a graph that maps all of this out. So the first thing let's look at is let's orient ourselves with the axes. So our x-axis is just our years, and so this one goes from 1900 to about 2020. Actually, it really goes to 2012. That's where it stops measuring it. And then our y-axis is our difference in temperature. Okay, it's a difference. Now, what I hate about this graph is that it uses Fahrenheit, but we have to stick with our unit. Remember, for science, especially in this course, we're really focusing on Celsius. But essentially what we can see is that in the 1900s, it started at some temperature. They just said this is 0, this is where we're starting at. And so through 1900 to about 1930, we saw a decrease. It was lower than the original temperature. Then from 1940 to about 1980, we saw an increase and decrease. So it went up and down, very, very small. And then we hit about 1980, and it has just steadily increased, okay? Continually increased. It's gotten warmer and warmer and warmer. So since 1900s, or down here at the very lowest to the very, very top, we've seen a difference in temperature at about 2 degrees Fahrenheit, which is close to 1.2-ish degrees Celsius, and it's not perfect, but something around that point. So we have seen a significant increase in our temperature. Now, like I said before, that doesn't sound like a lot, but for certain parts of the globe, that's a lot. It's a bigger difference. So let's look at a map here. So what we're looking at here is a difference in temperature. So again, we're mapping the change in temperature. This is the years from 1950 to 1980. And what we're mapping is, this is versus 1950 to 1980. These are actually a map of 2005 to 2009. There we go. And what we're looking at is the difference in temperatures that we've seen. And so at the bottom is our little scale. And so when it's the blue and purple, we've seen a change in temperature of -4 degrees Celsius. When we're at the deep red, we see a change in temperature of +4 degrees Celsius. So it's gotten warmer and warmer and warmer. So now looking at this graph, I want you to look at it and answer a question for me. Where do we see the biggest changes in temperature? Go. All right, did you get an answer? Hopefully you did. Essentially, where we see the biggest changes in temperature are in our higher latitudes, okay? Our higher latitude. So specifically, if we're looking at this graph, we see it around our North Pole. So at the very, very top here, we see a change in temperature of about 4 degrees Celsius. That's a big deal. Have you seen those commercials where they have the polar bears on the ice patches and it's melting and they can't get off and they're sad? Or you see these penguins and they look just like miserable. And I love penguins in case you haven't figured this out. But we are causing our glaciers to melt and we are destroying the environment up at our poles. These polar bears and penguins cannot survive because there is not any ice. There's literally no place for them to live. So when people are saying, oh, it's just 1 degree here, it's 0.4 to 0.8 degrees Celsius, that's not the whole story. That's the global average. And there is a huge difference in temperature between something in the South Pole and something at the equator. So please keep that in mind. Take care of yourself, guys. Drink water and have a great week.